In this video, we'll run through the basics of linear models for the Recursion and Financial Modelling core unit in further mathematics. So firstly, what do we mean by linear models? In this case, we're talking about those recurrence relations that have a constant increase or decrease. So linear growth or linear decay is defined as each successive term in the sequence found by adding for growth or subtracting for decay a constant value. And we have our general forms of those recurrence relation rules there. So you can see in both instances we have this constant value of D. When it's being added, we've got growth. When it's being subtracted, we have decay. The common applications that we look at in further maths are flat rate depreciation, unit cost depreciation, and simple interest loans and investments. So there we have decay in terms of depreciation, flat rate and unit cost, and we have growth modelled by simple interest loans or investments. So firstly, a closer look at linear growth. When we are talking about the recurrence relation form, we can see there we are always giving our recurrence relation as V0 equals, or our initial term, and then stating it as the next term, so Vn plus 1 is equal to current term, Vn plus D in this case. So for example here, we've got a sequence where T0 is 10, so our starting point is 10, and then our rule is given as the next term is equal to the current term plus 3. So if we were to write out those terms, obviously starting with 10, and then next term would be the current plus 3. So in this case, 13. Then again, the next term, the current plus 3, so 16. The next term, the current plus 3, gives us 19. So we end up there with our sequence as 10, 13, 16, and 19. If we were to consider a graph of that sequence, we can see it forms a straight line because it is that constant increase, and that gives it its linear name. We have that linear constant growth. If we were to transform this to a general rule form now, where instead of finding it recursively, if I wanted to be able to find what term 10 was or term 100, I want it in general rule form to be able to do that efficiently. So we take the main components here from our recurrence relation, being our value of V0 and our value of D, and we pop those into this general rule in their places. We substitute those in. So with the example we have here, where T0 is 10, D is 3, we take those values, and that makes our general rule Tn equals initial value plus D times N. And so now if we were in a situation where we wanted to find T12 is 10 plus 3 times 12. So we're substituting in that value of 12, both in our notation and in our rule where we see N. And so in this case, we end up with T12 is 46. So simple interest is our application in further maths that we look at with linear growth. So our balance is increasing at a constant amount each time, and that's regardless of whether we're talking about a loan, where the amount we owe is constantly increasing, or an investment, where the amount we have earned or our balance of our investment is also constantly increasing. And so again, our recurrence relation form and our general rule form are the same as they were for that linear growth. A couple of different things here. When we're talking about V0, that is often referred to in a question as the principal value, okay, the initial amount or the principal value, so looking for those keywords. When we're finding that value of D, often we are given our simple interest as a rate, a per annum rate. And so in order to calculate the constant amount, we need to use the formula that is here, looking at where D is equal to R over 100, so that rate over 100 times our principal value. Obviously, R is our interest rate, and VN is the value of the investment or loan after N time periods. The time periods for the rate and the value of N should be the same, and if not, we may need to adjust. We'll look at that in an example. So things you are looking for in a question is obviously the key phrase or words simple interest. Okay, sometimes it is though referred to as flat rate interest. So you're definitely looking for that absence of the word compound. That's another useful thing to look out for. Be careful not to confuse just because you see a percentage rate that it's compound interest. Be really careful that you're checking what the key words are. They will always identify for you what you are doing. And a hint here, when you are working through a question like this, you need to calculate or identify your value of D first, and then put it into the rule form that you need to answer the question. So here's an example of an exam question. We don't often find simple interest asked on its own in our exams. So more often than not, it's part of a combination where we are charging interest and making repayments, or it's in conjunction with other things. So here's just one example of how we can go about answering a simple interest question. So an amount of $6,500 is borrowed, and it is borrowed at a simple interest rate of 3.5% per annum. So note there, they're telling us it's simple interest. The total interest paid over the period of the loan is $910. So in total for the life of this loan, there was $910 interest charged. What we are asked to do is find what is the period of the loan. So firstly, let's think about this 3.5% per annum. So how much are they charging per year? And so in order to work out that, we're being asked for D. And remembering that D, if we take our initial value and multiply that by our rate. So in this case, $6,500 times 3.5 over 100, we find that the amount of interest per year is $227.50. And so if that's how much interest per year is being charged, we have been charged a total of $910. So how many years worth of interest is that? So our total interest, 910, divided by 227.50. And we find that that gives us 4. So that means there was 4 years worth of interest added to that amount. Next, let's consider linear decay. So this is a sequence where we are decreasing. So again, very common components here. Our recurrence relation form, we're still giving our initial value, and we're giving it in the form Vn plus 1 equals Vn minus D this time. So we've got that decreasing value. So for example, we have P0 is 20, so our initial term is 20. The next term is equal to the current term minus 4. So if we were to write out those first four terms, remember starting with our initial value of 20, our next term would be the current minus 4, so 16. Our next term, current minus 4, so that gives us 12. And again, current minus 4 gives us 8. So our sequence there, the first 4 terms, would be 20, 16, 12, and 8. Again, we can graph those, and you see, once again, we're talking about a linear, a constant decrease. So we have that negative straight line formed with that graph. When we transfer this into a general rule form, again, we're taking our value of our initial term V0 and our value of D, and being careful that we are decreasing. So it's minus D times N this time. So picking up our example here from Pn, we would find that Pn is equal to our initial term 20 minus the value of 4 times n. And so in this case, when we're wanting to find P12, again, where we see n, we are substituting in the number 12. So in this case, 20 minus 4 times 12, which would give us a value of negative 28. So for our main application of linear decay, we're looking at two key types of depreciation. So just a quick reminder, our depreciation refers to a reduction in the value of an asset over time, in particular due to wear and tear. So the two models that we will be looking at now, as said previously, is the flat rate depreciation and the unit cost depreciation. These are both examples of linear decay. The third model, reducing balance, is an example of geometric, and we'll look at that in the next video. So flat rate depreciation, we are talking about that constant decay. So again, our recurrence relation form and our general rule form are the same as what we looked at for general linear decay. When we're calculating that value of D, once again, we quite often are given that as a rate of depreciation, and it will be clearly stated to you that they are using the flat rate method, or that the rate is a percentage of the initial value. So you want to be looking for those key phrases in the question so that you can identify that you are using this form of depreciation. Again, your first step should always be to either identify or work out our value of D first, and then apply that in the rule form required. So an exam question here, Ray paid $40,000 for new office equipment at the start of 2017 financial year. At the start of each of the following financial years, she used flat rate depreciation to revalue her equipment. At the start of the 2020 financial year, she revalued her equipment at $22,000. The annual flat rate of depreciation she used as a percentage of the purchase price was. So in this question, we've been given quite a bit of information and we need to work out what exactly they're asking us for. So in this case, we have an initial value. So we have a V0 value of $40,000. We have a value after 3 years. So we have a V3 value of $22,000. And we're being asked to find what is the rate of depreciation as a percentage of the purchase price. So we're being asked to find that little r value, that percentage. Another hint is that all of our answers obviously have percentage signs, but just making sure you're finding the rate, not the actual dollar value. So firstly, we're going to do that by finding out, well, how much did the equipment depreciate by? How much did it depreciate by per year? So what is our value of D? Once we have our value of D, we can then set up an equation to solve to find this percentage R. So firstly, how much did we depreciate by in total? So our value dropped from 40,000 down to 22,000. So how much did it drop? 18,000 in total. Over the 3 years, that means if we divide that value, 18,000 by 3, it was depreciating by $6,000 per year. Okay, so that is our value of D. So now we can set up an equation to solve. If D is equal to our initial value times R over 100, we've found that D is 6,000. Our initial value was 40,000, and R is our unknown, what we're solving for. And so remember, we've always got our CAS calculator to help us solve here. We can find that R is equal to 15. And so that means my annual flat rate was 15%. Another example here, we have Jeff who purchased a computer for $4,500. He will depreciate the value of his computer by a flat rate of 10% of the purchase price per annum. So that's a different wording of our flat rate depreciation. The recurrence relation that Jeff can use to determine the value of the computer after n years, given as Vn, is, and we've got our options there. So firstly, we want to be able to identify that we are talking about flat rate depreciation. Flat rate depreciation means that we should have a format of our rule that looks, our recurrence relation should look like this, where our next term is the current term minus D. So if we look at our options here, there is actually only at the moment one option that looks like it's in the correct form. But sometimes we may have two options, or we may want to know how can I actually find this rule if it's not a multiple choice question. So in this case, we want to use the information provided to firstly calculate our value of D. And so for that, we need our initial term and we need our rate, flat rate depreciation. And so in this case, our initial term, 4,500, times our rate of 10 over 100 gives us a depreciation value of $450. So we are depreciating, so decay, decreasing by $450 per year. And so that's why we can now be sure that A is our correct format. All of our options had the initial term as 4,500, so that wasn't a way of eliminating. If we look at the other options, B is similar, but we are adding, so that's increasing, not depreciation. C is a geometric style. It is decreasing, but geometric. D is another geometric increasing, and E is a little bit of a combination of both. So it's important that we now get used to, when we identify we're talking about flat rate depreciation, we are looking for our rule and looking for what information do I have and what do I need to put in. Moving now to unit cost depreciation. So we're still talking about the decrease of the value of an asset, but now it's in relation to the units of use. So sometimes that is a machine, and every time it is used, it loses a certain amount of value. Or maybe it's about distance travelled. They're the two common types. Again, we're looking for key phrases. So our recurrence relation and our general rule form are exactly the same as flat rate, but you're looking for this phrase unit cost within the depreciation. And once again, your first step is always identify that value of D and make sure when you're putting it into the rule, you're getting a decreasing amount. So in our example here, we have a photocopier that is depreciated by 4 cents for each copy it makes, or $0.04. 3 years ago, the photocopier was purchased for $48,000. Its depreciated value is now $21,000. The total number of copies made by this photocopier in the 3-year period is, so firstly, we want to work out, well, how much has it depreciated, the copier, and then we can divide that value by its depreciation per use. And that will allow us to work out how many uses or how many times it was used in that time period. So the 3 years here is actually not relevant information, but the two values and the unit cost is. So this value here is what we call the unit cost per use of the unit. So firstly, if we started out with 48,000 and our value became 21,000, that means our photocopier depreciated by $27,000. If it depreciated by $27,000 and each unit is worth 4 cents, when we divide that, we get 675,000 uses. Or in this case, this context, 675,000 copies made. So that gives us our answer as E. A final example, we have a delivery truck was new when it was valued at $65,000. The truck's value depreciates at a rate of 22 cents per kilometre travelled. After it has travelled a total distance of 132,600 kilometres, the value of the truck will be. So firstly, make note that we are talking about a dollar amount for the value, but then the unit cost, they've quoted that to us as cents. So we actually want to change that and say, well, our unit cost, our value of D is $0.22. We want to know what the value will be after having travelled 132,600 kilometres. So our value, effectively, I'm using a general rule and finding out the value after that 132,600 kilometres. Initial value, 65,000, multiplied by our value of D, 0.22, subtracting our value of D, 0.22, times the kilometres, 132,600. And that will give us a value here of 35,828. So being E as our answer. So just a really quick rules recap here. You'll note both versions of growth and decay are very similar in their rules. So be very careful when you're reading the question, you're picking up keywords. In particular, you're looking for those key applications. For growth, we are talking about simple interest, either loan or investment. Both will be growth. And for decay, we are talking about the flat rate depreciation and unit cost depreciation. And just remembering that your value of D can be, first you have to calculate it if you're given that as a rate of the initial value and using that rule there. Okay, that's it for this video. Good luck.